So welcome back, everyone. So next session, we have Professor Shailesh Chandrasekharan from Duke University. So Shailesh is going to talk about qubit regularization of asymptotic freedom. Shailesh, please.
Yeah, thanks, Anosh, and thanks the organizers for giving me this opportunity. So I want to talk a bit about a slightly new idea that we have been exploring. I would say people at Los Alamos, Tanmay Bhattacharya and Rajan Gupta are at Los Alamos. Harsh Singh was a student of mine who's now at the Institute of Nuclear Theory in Seattle. And then Alex Buser is a student at Caltech. He's John Preskel's student. So we are basically trying to think about quantum field theories that will be usefully formulated on a quantum computer. And as David mentioned, and there have been questions about sign problems, one of the ways perhaps maybe in a distant future is to solve all of our interesting quantum theories on a quantum computer that might then help us overcome some of these computational bottlenecks that we all have at the moment. So that is sort of the motivation. So let me begin with this motivation further. So if I recently came across this talk by Richard Brower, who mentioned about this paper where Feynman sort of explored this whole idea of simulating various quantum systems using computers. And in a sense, he was thinking about quantum computing at that time. And Richard pointed to me interesting question going back to sort of, I would say, 1981 now, where Feynman asks this interesting question. So he says, the question is, if we wrote a Hamiltonian which involved only these operators, that means he's talking about these quantum spin-half operators, coupled to corresponding operators on to other space-time points, right? So he's thinking about every space-time point to have these quantum spin-half operators. The question he's asking is, could we imitate every quantum mechanical system which is discrete and has a finite number of degrees of freedom, right? And he says, I know almost certainly we can do this for any quantum mechanical system which involves Bose particles, but then he's not sure about fermions. So in a sense, this is exactly what quantum computers are going to help us if we can formulate theories. On the other hand, notice that at that time, Feynman was just thinking about a finite number of degrees of freedom, right? But if you think about trying to do this for quantum computers, then you come up with an important bottleneck. The bottleneck is that especially Bose particles, right? Fermions, you might say, are basically qubits because there are only two states of a fermion on each space-time point. And so in a sense, it's like a finite dimensional space. However, bosons, at least the way we formulate it using quantum fields, is to incorporate them with this commutation relation, which can only be realized in an infinite dimensional space. So by construction, a bosonic quantum field theory is constructed, at least in some naive sense, using an infinite dimensional space. So there is a local infinity in the Hilbert space dimension, right? And the question is this infinity necessary, or can we regulate that infinity and still get the physics that we are after? So that's sort of the basic idea that we are trying to explore. So the goal is to construct a lattice Hamiltonian with n qubits on each lattice site, which gives us back the same continuum quantum field theory using our lattice formulation as we usually would like to achieve, right? So this n qubits per lattice site, of course, makes the whole theory finite dimensional, and maybe one can formulate it on a quantum computer, right? So you can imagine that if you had n qubits, since each qubit is a spin half degree of freedom, you have 2 to the power n dimensional Hilbert space on each lattice site. So basically, this field of research has become interesting, I would say, in the last 5 years or so, things are growing exponentially. There are two ideas I would say to explore here. One I would call the qubit truncation approach, which is basically trying to tell you that we know what the theory is, right? So we begin with a traditional lattice Hamiltonian that we all know or we have formulated and studied before. But then since we want to think about this theory in a finite dimensional Hilbert space, we truncate that Hilbert space in some way to an n qubit Hamiltonian. Right? So that is what I call a qubit truncation. So basically, the Hamiltonian is given to us. We know what to do in the usual traditional approach, and we're just going to truncate it. But in this approach, as you will see in a moment, there is a slight difference in the way in which we think about continuum limit. A different approach is to think about a regularization. So think about exactly like how we thought about regularizing space-time on a lattice. You can think about even regularizing the infinite dimensional Hilbert space on each star. So here you explore the space of n qubit Hamiltonians to reach the continuum limit, right? You don't, you look at it in a different way. So the difference between these two approaches, in my opinion, is that in this case, the n that you have, we know the continuum limit exists when n becomes very large, and then we take a to 0, right? So this is going back to the traditional approach, except that we may have to take n to infinity before the continuum limit arises. Whereas on the other side...
Shailesh, Simon has a question.
Sure, yeah, go ahead.
Hi, Shailesh. Is this not similar to the way we talk about the renormalization group? I mean, we know we can do, say, lambda pi fourth with Ising spins.
Yeah, so this is exactly the point.
So is this the same kind of idea?
This is exactly the same idea. So exactly as you were saying, here the question would be, can I fix n finite and still take a to 0, exactly like what we would do, just tune our couplings, find the RG fixed point, and then do the theory like that. So go ahead.
Go ahead. Is it okay to ask? Maybe you can first finish, sorry.
Yeah, please ask.
Okay. So it's maybe just a technical question, but related to motivation. So in qubit regularization, so you have only one limit, continuum limit, like usual lattice gauge theory. And in the qubit truncation, of course, we have to send this truncation level n to infinity. But when lattice, at least if we take n infinity first and then a to 0, there is no additional fine tuning or something when you break. So this truncation in principle breaks symmetry. But unlike continuum limit of lattice, this truncation of Hilbert space does not introduce complication in principle. It's just maybe computationally hard or something. I mean, that you had the two steps make any complication or not. I don't think there is any additional complication in principle.
No, you're right. So in principle, if you truncate it in a natural way, for every n, you will be able to define a theory and study the theory, except that maybe the a tends to 0 limit may or may not exist in the usual tuning of the coupling. You may have to find some new ways to do it. And in some cases, you may not even find a continuum limit in that kind of truncated Hamiltonian.
Yeah, I mean, but look at every lattice theory has a different ultraviolet behavior. So of course, it's every lattice theory screws up the ultraviolet. So the question is if the infrared is universal, and that's. But there's no correct lattice theory.
Yeah, of course. That it's okay. Yeah. So but anyway, so in principle, both approach can work. In principle, and qubit regularization may have some advantage depending on the example, I guess.
Well, I'm not. This is more of an academic thing. So I'm just saying that typically the approach is that you write down your Hamiltonian in the traditional way, and then you just truncate it. You don't think deeply about exploring the space of Hamiltonians. In principle, you could do that, and then I would say you are getting into this realm. That's all.
I think in principle you always do that. The Ising model is not 5-4 theory. You always have to invent a completely specious ultraviolet theory. Wilson links are not part of QCD. They're just specious.
I completely agree with you, Rich. I don't think that's an argument. I completely agree with you. There's no question about that. Yeah. So so all I guess I'm trying to say is that if you use the traditional Hamiltonian and try to truncate it, in that truncated space, you may or may not have the right critical behavior. That's all. That's the whole question. Okay. So typically what people do is try to argue that maybe at some n tends to infinity, there is a critical point. So you may be able to explore that in this truncated theory. And in principle, that may be possible. I'm not denying that. So the idea about qubit regularization is that to think about theories with an n-qubit model, essentially on a lattice, and try to see if the continuum theory exists in that n-qubit model space, right? So I would say that this is more like a particle physics perspective, where we believe that we know what the continuum Hamiltonian is, right? And so we just have to truncate it in some way to do calculations, so regulate it in that language. This could be thought of as more of a condensed matter perspective, where you actually design the material with the right lattice spacing, the right lattice structure and the right interactions, such that you get at a quantum critical point the continuum limit that you want to do. So let me tell you briefly about the qubit truncation, because that's what many groups are exploring. So this is actually the simplest approach. So basically take that favorite lattice Hamiltonian that you get, and then you write down a simple realization of that in the n qubit space. And of course, as I just mentioned, as n becomes large, you don't know whether you get back a point in that space of models where you really get a continuum limit. And that's an interesting question. Now, it's important to distinguish two types of quantities. One is the lattice quantities, where you sort of match something maybe in the traditional model with the qubit model and see whether those quantities match up or not. And this is exactly what most people try to do because they are easy to do, right? So this is easy to check. However, as I mentioned, the more important quantities from at least the QFT perspective are universal quantities, which you need to be sure that you get back your original theory. And for that, you need to be able to, again, really go to the continuum limit, or at least close to the continuum limit in the scaling regime to be able to see this works out. And that's harder, and that's typically not easy to do. So many QFTs are being formulated using the qubit truncation approach. So it all started with scalar field theories. And then more recently, people have been exploring gauge fields. There are also people exploring some kind of discretization or digitization where the original symmetry is broken, but into a discrete subgroup. And then the hope is that as you make n larger, the discrete subgroup becomes larger and larger. So for example, U1 is being explored as Zn, for example. And then the question is, as n becomes larger, does the U1 emerge quickly? And then once you formulate it, then of course one needs to ask how do you study these theories? And there's a lot of work using tensor networks, at least in lower dimensional systems, that seem to be useful in understanding the physics of these qubit truncated models. And there is some evidence that as n becomes large, these qubit truncated models actually approach the traditional models, at least for these local lattice quantities, exponentially. So there is some reason to believe that a small n may be sufficient. However, an important question is to make sure that the universal quantities also obey the right properties. And the recent paper by Paulson et al. Actually show you that this truncation might reproduce some good physics in some regime, but not the right physics unless you change the truncation. So this is I found this paper very interesting to think about how to think about the truncation approach. However, what I would like to talk about in this talk is slightly different. I would like to think about what I call the qubit regularization of QFTs. And as I told you, the view here is that the truncation of the Hilbert space per lattice site is a new type of regularization. And that is something that is going to be important for quantum computation, right? So in addition to the lattice, you have to even think about formulating the theory with a finite dimensional Hilbert space such that you reproduce the original quantum field theory. And the first attempt of this was done in this paper. So if you think about the original QFT as sort of the goal or the target, we already know how to do this using the usual lattice regularization, where we start with our Hamiltonian or a Lagrangian, depending on how you want to think about it. And then we just tune our couplings such that we get the continuum limit, right? So the qubit regularization is exactly the same idea, just that in addition to the lattice, you also have a finite dimensional Hilbert space per lattice site, right? And then again, all you do is tune couplings. You don't change the number of qubits after that, right? And then ask if there is a RG perspective, as Simon pointed out, that gives you back the original QFT. And the question is, does the original QFT exist in this n qubit regularization space? And that is not always obvious, and that's sort of the interesting question. So from the RG perspective, the idea is the following, right? So you have some kind of a theory in some space of all possible theories, right? And the quantum field theory that you're interested in appears in the vicinity of some fixed point, right? So the question is, how do you get to this fixed point? It's typically very hard to really get to the fixed point because it appears in some complicated point in your theory space. What one does is write down a simple lattice model, right? And then you tune the lattice model to what we call a quantum critical point, where you get long correlation lengths compared to the lattice spacing. And so then the question is, at that critical point, the long distance physics is then governed by this fixed point, right? So in the vicinity of this critical point, you'll be able to study the physics of this quantum field theory in its vicinity. That's the traditional approach. What we are saying is, well, maybe an n qubit regularization exists, which is maybe completely different from this original model, but which also has the right quantum critical point where the low energy physics is exactly the same as this QFT. Right? So that's basically the idea. So all this was done long ago, actually, in what we call the D theory approach. So here is a reference to this almost now 15 years ago, where the idea here was that you again formulate the theory with n qubits, but then in this case, allow the n to grow naturally if needed, right? It's not necessary. We may be able to achieve this without n needing to grow. But in the D theory approach, there was an additional dimension. And that dimension could be thought of as the number of qubits in a sense. And you could allow that to grow. And if you did that, then there was ways of showing that even asymptotically free theories and a whole class of theories, almost all quantum field theories, could be reproduced using this approach. And so, for example, in 2006, these authors showed that the asymptotically free CPN models could actually, in 2 dimensions, could actually be reproduced by making n grow with in some way, right? So as you make n bigger and bigger, exponentially the theory converges to what you really want. However, it was not clear at that time that can you keep n fixed, right? You don't let n to grow. Can you really reproduce the asymptotic freedom with a finite n? And that is sort of the new sort of idea. Can we reproduce asymptotic freedom with n finite? And in that sense, I would say that's the qubit regularization picture of these asymptotically free theories. So are there questions so far so that I can go on? Okay.
Yeah, why does increasing n basically help you to reach the required quantum field theory? What is the logic behind that?
But remember, the original quantum field theory was defined with n equals infinity. That is the usual commutation relations of bosonic fields, right? So it is very natural that at very large n, you will get back your original theory. So the question then is, can you then formulate your lattice theory such that as n becomes larger, you quickly reach what you want to reach? That's the question. Okay, so let me go ahead and try to give you, explain all of this in the context of the simplest O3 model, right? So this is basically a scalar quantum field theory. And in the traditional formulation of this theory, what one would do is one would start with an action on a space-time lattice, where phi is basically a unit vector, right? G is basically what we call the lattice coupling here. So X is a point in space-time. So it is D plus 1 dimensional Euclidean lattice, basically a hypercubic lattice, if you wish. And then you write down a nearest neighbor action with just the dot product. This is just, I'm sure all of you know about this. This is basically the way we think about ferromagnetism in spin models, right? So this is basically a lattice model to begin with. What we will find is that as you tune G, there is a particular point where a continuum limit can emerge from this theory. And at that particular continuum limit, you get an interesting quantum field theory. Now, if you think about this Lagrangian model in terms of Hamiltonian model, because at the end, in the qubit formulation, we're going to be thinking about Hamiltonian formulations of these theories. So if in a Hamiltonian model, this Lagrangian model actually is written in terms of not just phi, but remember in Hamiltonian, you have to write phi and pi as conjugate variables. So this phi and L, the generator of rotations in this O3 space. So these are, that's why they're called quantum rotors. So this is basically a rotor model where this G just appears as coupling in this model. So again, as you tune G, this is basically the same model. So you will see that there is a continuum limit, and one can see that that continuum limit is a quantum critical point in this Hamiltonian version. That's one way to think about it. So QFT emerges at this quantum critical point, and the phase diagram is the following. So in D equals 2, that is 2 plus 1 dimensions and 3 plus 1 dimensions, right? As you change G, there is a critical point that distinguishes between a phase where the O3 symmetry is spontaneously broken with Goldstone bosons, and a phase where the O3 symmetry is preserved and you get a massive theory. At these points, away from this critical point, this mass scale is going to be pretty large. In some sense, it's going to be at the cutoff scale. So from a quantum field theory perspective, this is just a lattice theory, and the real continuum physics only appears at this particular point. So this side of the theory gives you a massive quantum field theory as you approach this particular point, and this gives you some kind of a broken theory. And so this critical point is very interesting. It's called the Wilson-Fisher fixed point, and there you get a Wilson-Fisher conformal field theory. In 4 dimensions or 3 plus 1 dimensions, you get basically free field theory. This is basically the Gaussian fixed point. So if you want to study scalar quantum field theories, typically one starts with this traditional model and tunes G's to this close to this critical point where you get back your continuum field theory. Now, D equals 1 or 2-dimensional O3 model is much more exciting and interesting. There, this critical point is sent all the way to 0, and you basically get a massive theory everywhere. Further, this mass generation, while here in, for example, 3 dimensions, the mass has an anomalous dimension, which is like a power law. Here, this coupling becomes marginally relevant. So in fact, this is exactly the asymptotic freedom of the O3 sigma model, right? So if you want to study the asymptotically free two-dimensional O3 model, you can start with this two-dimensional theory, which I wrote in the previous slide, and just tune yourself to G equals 0. Close to G equals 0 will be your massive asymptotically free O3 sigma model. So the question which we'd like to explore is, can these physics close to these critical points that we can define from our conventional traditional model, which lives in an infinite dimensional Hilbert space, can be reproduced in a finite dimensional Hilbert space? So to understand this a bit better, let's think about the qubit truncation method first. So the Hilbert space per lattice side of the traditional model can be understood as follows. You think about the phi. Remember, phi is one of the variables in our theory. And so it's a point in your space, right? And so if you think about the Hilbert space, that Hilbert space lives in an infinite dimensional Hilbert space at every point on theta phi, right? It's a point on your sphere. And so and it lives on an infinite dimensional space at every space-time point, right? Now, if you think in the conjugate variable language in terms of the eigenstates of L is an angular momentum, essentially. So you write it in terms of the basis of L and M. And so again, that infinite space can be written in terms of L and M, which is a discrete basis, but still infinite dimensional, right? So these two are sort of conjugate with respect to each other. So the minimal truncation would be where you allow L equals 0, right? It's just the singlet, and the L equals 1, the triplet. Remember, if you just had L equals 0, then there is nothing in the theory, right? Because you just have the singlets at every space-time point. There's no dynamics to think about. However, if you have L equals 0 and L equals 1, then there could be dynamics in the theory, right? So at every space-time point, the minimal truncation of this theory would be with a 4-dimensional Hilbert space. That means you can realize it using 2 qubits, right? So those 2 qubits can be thought of as spin halves. I can make them into a singlet or a triplet. And so we can imagine that we would like to reproduce our physics using just 4-dimensional Hilbert space at every site. Now, is this possible? That's an interesting question to ask. So the question is, are 2 qubits per lattice site sufficient to recover the traditional O3 quantum field theory? So the classical vector is being replaced by just 2 qubits, right? This is an infinite dimensional object in quantum mechanics, whereas this is just a finite dimensional space. Now, if you think a bit, indeed, if you are able to find a critical point where you get back your original quantum field theory of interest that separates 2 phases, right? So basically, I'm looking for an IR fixed point where at a quantum critical point that separates 2 phases, then that should be easy, right? So all I need to do is to write down a model where there is a massive phase and a broken phase, a spontaneously broken phase and a symmetric phase. And if the theory has a second order phase transition, and if quantum field theories emerge at that second order phase transition, that should not depend on the details of the theory, right? That's the basic understanding from RG. So that should be easy to recover. And this is exactly what Richard pointed out about the Ising model being, you can obtain it using just a discrete set of degrees of freedom. In fact, we also know that many other theories can be obtained, but just we wanted to explain that this is possible just from simple physics, right? So these two are very easy, and in this paper we actually showed that is possible. The more interesting question is whether asymptotically free theories, which do not arise in this particular way, right? They seem to arise in a much more non-trivial way at the endpoints of some phase diagram. That seemed much more difficult, and it seems indeed not very obvious how to achieve that. Right. So let me quickly go through what we did before and just convince you that the Wilson-Fisher fixed point, for example, is easy to obtain. Right. So, and it also give you some sense of what type of theories we are going to explore for the asymptotically free theories. Right. Because that's the more interesting part of the talk. But let me just go through the more simpler ideas first. So if you wanted to reproduce the Wilson-Fisher fixed point, this should have been 2, for example. In D equals 2, this critical point has been studied extensively, right? So as I told you, there are 2 phases of the theory. One is the symmetric phase and one is the broken phase. And all you need is to find a quantum critical point that separates these 2 phases. At that phase transition, you can actually study some quantities. For example, here we will focus on the susceptibility, which is basically the integrated autocorrelation function, right? And then that susceptibility is supposed to scale in this simple scaling form, right? Where eta and nu are scaling exponents, and these have been obtained with great precision by various authors, and you can find more details about this in this simple review article. Now, what about the qubit regularization approach? So in the qubit regularization approach, remember that we are going to replace this model, the traditional model, with just 2 qubits. So we are going to have singlets as states, which we will view as a Fock vacuum state, right? And then the triplet will be spin 1 particle moving around on your lattice, right? So these 2 are the degrees of freedom we will try to start with, right? So from the perspective of the Hilbert space, you have Fock vacuum states or spin 1 states. And then we write down a simple Hamiltonian that only preserves the symmetry of O3, right? So it should be O3 invariant, and that's all we preserve. And there are various, of course, ways of doing it. So we just did a very simple model where we had Fock vacuum states, and then we had particles hopping around on your lattice, right? This is time, that is space. So the particles hop around, right? So you can have a spin up, spin z equals.
Let's ask a simple question. So the Hamiltonian you wrote, is it formally the same as a qubit truncation approach, except that truncation level is lower, or it's a different Hamiltonian?
It's a different Hamiltonian. It's a completely different Hamiltonian, just motivated by symmetries. Exactly. Mm-hmm. It's not the original Hamiltonian.
So if you just use a qubit truncation approach, but fix truncation level and then take continuum, then you end up wrong.
No, you will, even there, you might be able to do this. We didn't do that, but for this particular problem, it's easy. I will show you for the asymptotically free theory what happens.
Okay.
This is much more easier. So we can actually do it in many different ways. And I'm sure the qubit truncation approach, as Rich already pointed out, there is a way of going between the 2 phases, even in this particular thing. Rich, you had a question?
Yeah, but the truncation is done here in momentum space rather than X space. I mean, you don't take the Q variables and truncate, you take the P variables and truncate them. That's a big difference.
Yeah, that's definitely a good point. I think that's a good point. That's a very different truncation. So here, to maintain the symmetries, we truncate into the L thing, not in the or not in the X. So maybe I should go back and go to that slide. That's it. Whoops. Yeah, let me remind. Oops, maybe it was even before that. So here, what Rich is saying is, you are not truncating it in this space, right? Because this is like a whole sphere, and you could say, well, I will pick only a discrete group in that space, and then slowly make that group bigger and bigger. That becomes much more non-trivial for symmetries like O3, right? There aren't many subgroups that you could think, perhaps. And even then, and each subgroup that you pick will break the O3 symmetry. And that can lead you to a different critical point. So that's why we choose this, because we can truncate it in an L space, which preserves the O3 symmetry, because each L is invariant in that subspace.
Okay,
that's sort of the basic.
Thank you.
Okay. So here, since you've truncated with the L in the L space, we can preserve the symmetries exactly, and then we just pick the most simplest kind of model, which is easy for us to do a quantum Monte Carlo on. And so we just pick a model with hops. And then we also allow for pair creation events, right? So this is very simple, and you can think about it as though there are spin-1 particles in your theory. There's a Fock vacuum state, and then there are spin-1 particles that can exist for some time, and then they can annihilate and create, and so on. So it's exactly like how you would write down simple Feynman diagrams. And in fact, if you try to start with this Hamiltonian and write down your partition function.
Hi, I had a question.
Sure.
The Hamiltonian that you have written, what are those other two terms that you have there? And how is that O3 invariant? The one on the...
Yeah. Good question. So, okay, so this, you see, the way I've written this down, this by definition, since the sum over M is O3 invariant, this is like the subspace either in the singlet or the triplet space. Here it's only the triplet space. These models are basically, you can actually write it down in this particular way and show that these are also invariant under O3, because you can make O3 invariant operators by summing over M, or you can also have M minus M, and then you can put a -1 to the M, and that's also invariant under O3. So that is.
What are those H? But what are those H? What does those H correspond to? I mean,
Okay.
what you have written down there.
Okay.
The
So
H,
this is like a chemical. This is like a chemical potential term that says that every triplet comes with an energy JT. This is a hopping term that just allows for particles to hop, right? This term, this is H. And this is a pair creation term where a triplet and another triplet, you can define an anti-triplet as -M and a triplet as M, and then these two annihilate to give you Fock state, Fock vacuum.
Okay.
So this is a pair creation and annihilation term. This is basically a hopping term, and this is just the usual some energy. It basically gives you some kind of a mass to the triplet, if you wish.
Okay.
So these are basically the terms that I have in my thing. So these are the pair creation annihilation terms, and then these are the hopping terms. So if I think about the partition function itself, I can write it in Euclidean time, right? This is the usual way we do calculations. And so remember, the goal is to reproduce what you can reproduce in the traditional model using this qubit model, right? So the same physics that I get in the traditional model, in the infinite dimensional Hilbert space, I want to reproduce and show you that I can reproduce the same thing and get the same physics using the qubit model, right? And so we start with the partition function, right? And in this case, I can write the partition function as a sum of weights, basically Boltzmann weights for each of these hops. So these are all local objects. This is basically an epsilon in time, right? So I put it in like exactly like how you would do a lattice regularization. I start with my qubit Hamiltonian and write it in Euclidean time, in discrete time, right? And so there's a weight for a hopping, which as the particle goes in time, that is this diagonal term. This is this JT term. Then the particle can hop. This is your hopping term. There's a weight for that. And then there's a pair creation term here. Notice the loop. Here, for example, there'll be a pair creation. So every horizontal bond which creates a pair will have this weight. Every a vertical bond will have this weight, and every time the particle hops will have that weight. And you can actually show that there is no sign problem when I write it in this language. And for every configuration, there's a weight. And you can, for convenience, we said JH equals JP equals J. So all these horizontal bonds will have the same weight, right? It's epsilon, oops. It's epsilon JP or epsilon JH. Now it's epsilon J. Now there is a ratio. This is like the ratio, which is a dimensionless parameter between the energy of having a particle or not, right? Having this a triplet or not. And so that will be lambda. So we can actually compute a susceptibility. Remember, I showed you some scaling relations of that susceptibility in the traditional model. There is an analogous susceptibility in this model, and you can actually compute that. And we get basically, yeah, so this is the formula to compute it. And the way you compute it is you allow for creation and annihilation events in these world line configurations. I call this a world line configuration of these particles. These are the Fock vacuum states, and these are the particles that go along. Now we can actually, I will not get into the details of the algorithm itself. If you want, we can have that discussion during the discussion period. So we can actually, I can show you what the critical scaling was at this Wilson-Fisher fixed point. We chose epsilon of 0.1. Again, it shouldn't matter because again, we are looking only at the critical properties. We did a whole calculation with a large number of lattice sizes. And so we got where the critical point was, what the critical exponents were. And notice that they match extremely well with the traditional model. So this is all not at all surprising. I would say if you are a condensed matter theorist, or if you are a lattice field theorist who has some experience comparing quantum field theories formulated in different ways, this is pretty straightforward. It's completely reasonable. The challenge is the asymptotically free fixed point. The question is, can we reproduce the asymptotic freedom with just n equals 2? As I already mentioned, in the D theory approach, we can reproduce this as you allow n to grow. And in fact, we get exponentially good convergence as n becomes larger, right? So what happens with just n equals 2? Now, in the true qubit truncation approach, this particular problem was actually studied in 2019 by these authors, right? The publication can be found there. What they found was these are sort of their results from that paper. So this is with just the truncation that I just mentioned, L equals 0 and 1. This is what you expect in the continuum. This is the expectation in the traditional model, right? This is the result that they get. So don't worry about what exactly they compute. They compute some kind of gap, and they want to study it as a function of that lattice coupling. So if you're at the right continuum limit, you should be able to see this as this becomes large, right? That's where the continuum limit exists. And notice that this doesn't produce the result that you want at all. So in the traditional model, there was one coupling, and if you just truncate it, you still have one coupling. But if you just take beta very large in this particular case, you just don't get that physics. So clearly, you need to do something more. Of course, what they did was they let n grow. So notice that with keeping 0, 1, and 2, they do slightly better than this. And by, let's say, 0, 1, 2, 3, they're able to sort of start seeing convergence to the continuum result. So this is what is this exponential convergence, I would say, that by 3 or 4, you're able to get the result, at least in this simple model. Now, this is not supposed to happen in general. So there are other examples where, in fact, this other paper that I mentioned actually studies it in 2+1 dimensions, and things are much more complicated there. But at least in the n equals 2, maybe you won't get it. And that is what we all thought. Even in the D theory approach, we assume that even with just L equals 0 and 1, we may not be able to get the theory. The question is, can we really get this with 0 and 1? For that, we need to explore all kinds of models, right? To be able to get the physics. Otherwise, we may or may not get it. So that's the question. So this is the result from our new paper. So now I'll tell you in the next, I guess, 15 minutes or so, what we did. Now I may have to go a bit longer, but hopefully we'll see where we end up. Let me quickly tell you a bit about the challenge with these asymptotic freedom models, right? So this is more academic, I would say, but it's important to understand what the challenge is. I will not get into the details of the calculation itself, again, which is more challenging. We can have this discussion if you want after the during the discussion session. But let me quickly, in a hand-waving way, explain to you what the problem is, right? So in the IR fixed point, there were two phases, right? And so we could just tune ourselves to the critical point and we were done. Whereas asymptotically free theories, it's not clear what that critical point is. What are the two phases, right? So this is not obvious all the time. So we need to be careful and understand that a bit more carefully. Further, the problem with asymptotic freedom is a bit more challenging because an asymptotically free theory has, of course, an IR scale because it's a massive theory typically. So there is a mass scale that is generated. And so you want that mass scale to be very, very small, or in terms of correlation length, that correlation length, which is the IR scale, must be very, very large compared to the lattice spacing, right? The correlation lengths must diverge. And that is typically what we think at a quantum critical point. At a quantum critical point, all you want is a correlation length to diverge. But unfortunately, at an asymptotically free theory, that alone is not sufficient. You also have lots of UV scales at very, very high scales compared to the correlation length. For example, if you think about QCD as an example, there is, of course, the proton mass, which is coming from, compared to the lattice spacing, that proton mass must be very small. But then maybe the physics at 10 GeV or 100 GeV also should be physical, right? You shouldn't just say, I get the proton correct, but I cannot get the 100 GeV scale correct. Of course, at 100 GeV, you can use perturbation theory and maybe get the physics almost perturbatively. But from a conceptual academic point of view, you will need to get a lattice theory that reproduces the physics at 100 GeV or even 1 TeV. So even the UV scale must also be there on the lattice, right? So the rough scales go like this. So there is, of course, the lattice spacing where you see the n qubit physics, right? But then there are UV scales next, where you start seeing maybe the physics of 1 TeV or 100 GeV or something which is all physical, right? Not the lattice artifacts anymore. But then, of course, there is this 1 GeV scale of the proton, right? So there are a whole big range of energy scales you need to explore, right? So these are all physical scales in the lattice, not just the IR scale, which is what typically, from a condensed matter perspective, you would think about at the quantum critical point. So here is what you want to do. In a qubit regularization of an asymptotically free theory, you need to design a material that has the usual quantum critical point, but then also allows us to think about physics at very, very short distances compared to this, which is also physical. But then, of course, there may be scales at the level of the lattice spacing, which is unphysical, right? So the question is, how can we study all of these different scales quantitatively? Now, this was actually studied nicely using what we call a step scaling function, right? This was introduced by these authors.
Simon has a question.
Yeah. Question.
Myself. All right, there we go. Just a quick question. So I should think about this as almost like an improvement program, or I'm playing with the UV scale action in order to resolve details at different length scales, closer to the continuum in some sense. That's that way.
That's one way to think about it if you want. But the goal at the end is you're not trying to sort of perturbatively improve to all orders. You just find an n qubit Hamiltonian where you just tune your couplings again, find the right quantum critical point, and all the scales magically emerge. Right. That's
right. I could imagine that the quantum critical point has several relevant directions, and you're tuning more than one of them, right?
That's fair. That's one way to think about it, if you wish. But it,
yes,
it could be. That's why it is more subtle. Yes, go ahead.
Yeah. Sorry, I don't want to cut off Simon.
Yeah, I'm done. Thank you.
Okay, this is a really important point, and I'm trying to understand it myself. So let me raise this again. If you go to, 5-4 theory and you have the Wilson-Fisher fixed point, of course, you can get the massive theory by tuning in such a way that you have states and scattering and an S matrix and so on. So it's not true that you always go, bang into the conformal theory. So there are scales that you get. And in fact, if you look at the 04 model, you'll get the Higgs mass, right? And it's not even in your field. I mean, you had a spin in the Higgs mass, it's a fluctuation. So you do get extra scales even at a standard second order phase transition. So but there is a distinction here, and I'm trying to get it. I think it's a very important distinction with the asymptotic freedom. So how can you contrast it in that context?
Yeah, so what I would argue is that every theory, in some sense, if you can show that there is a continuum limit from this perspective, right? If it's a massive theory with a continuum limit, then we know that there are scales which arise at the infrared, which is basically the mass scale. But then there may be other scales in the problem, like as you mentioned, there may be a Higgs mass, maybe there is some resonance or something like that, which is at a higher scale. You want to be able to show that your original theory that you wanted, which had all these scales, be reproduced. And so you need to have some kind of an observable that allows you to do all those scales. I think that's and it's not obvious, as Simon pointed out. You may have to do some fine.
One difference. If you're in the situation of the 5-4 theory, you get a mass scale and so on, you get an S matrix and so on, but you do never get back to the perturbation theory. You do not know 5-4 perturbation theory. You know nothing about it. It's a non-perturbative problem. So you're saying the difference in asymptotic freedom, I think, is that you can probe the perturbative limit.
Yeah. So what I'm thinking is there is another way. There would be another traditional model that we all believe will give you the non-perturbative physics, and that non-perturbative physics is then reproduced in this qubit model. I would argue in that way.
But I'm saying in the case of the 5-4 theory, there is no perturbative limit.
There may not be any perturbative limit. That's perfectly fine, right? Even if there is no perturbative limit, look, perturbation theory is just a way of understanding the physics.
But in asymptotically free theory, there is a perturbative limit, isn't that?
Yes, so I will argue that. We will see that in a minute. You will see all that.
Okay. It's a very important point, Shailesh. It's really interesting. Yeah.
I think, Rich, what you're saying is, the log running, the nature of asymptotic freedom stretches those scales out. So instead of everything being clustered around some standard infrared scale, you can probe much further towards perturbation theory. Is that kind of what you're getting at?
Right. And in the perturbative limit, you get a fictional theory of color objects, which never get out, but nonetheless have physical meaning.
Yeah.
It's quite different, right?
Yeah, I would. Yeah. Can we have this discussion after it? I think this is very exciting. But
no, I'm sorry. No, sorry to interrupt, but it's a very important discussion.
If Anosh can give me more time during my time, then I would be happy to have it.
Sorry. Okay, I'll listen.
Yeah, Shailesh, no problem. Yeah. Take your time. Yeah.
So let me explain what happens in QCD, or in the O3 model, and then we will see how all of this can be extended to other theories. So in the O3 model, at least, of course, before I go, these kind of asymptotic freedom in either QCD or the O3 model have been sort of studied using what we call the running coupling. And in that context, an interesting function was defined by Lucier, Weiss, and Wolf, right? So let me quickly go through it. So what the idea is to compute what we call a mass gap, right, at a given finite lattice size. So L is a finite lattice size in our system, right? And then so that is a mass scale, and you multiply by L, so you get something dimensionless. So you define this dimensionless coupling at a given length of a box. You can think about these as physical objects, if you wish. You take a length of the box, right, put the system in a box, and then you measure some kind of a gap. And so then you can ask, what happens to this U if I simply scale L to S times L, so some scaling, right? You can actually argue that this object in this physical theory must be some function of U and S, because that's what the theory tells you it should be, right? You just take L, right, and you increase L to 2L, calculate this U again, right? And then that must be a function of U and S. And this is an important part of our asymptotically free theory. So this sigma S comma U is what is called a step scaling function. And for every asymptotically free theory, this is a well-defined function. It could be perturbative, it could be non-perturbative, but this is a very well-defined function. And this is called the step scaling function, and it's universal. So if you can reproduce this function using your traditional model, you should be able to reproduce that same function using your qubit model. And now notice that this particular thing has both infrared and ultraviolet limits, right? So for example, if I think about, since the theory is massive, I can make L very, 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 very large compared to the mass size, right? So then this M of L becomes constant. So in that limit of infrared, where L, the box size, is like a probe of the system, has become extremely large. Notice this is just a constant. So U times SL will just be S times U. So that's the infrared limit. And that has a very simple form, right? On the other hand, when you squeeze this whole box, right, to the ultraviolet limit, that's where you use some physics of asymptotic freedom and free field theory. And you can actually compute the sigma SU in perturbation theory, right? And there you can actually show that M and L scale with each other because M and L is actually a constant in that extreme limit. Because now it's a conformal theory, at least in that simple free field language, right? It's the coupling is marginal, so the whole thing is conformal. And so you can actually compute this object in perturbation theory. The sigma naught S, sigma 1s are all numbers at the end of the day that depend just on S. In fact, you can obtain that using beta function, right? So you basically know this function in both these limits. Remember, U tends to infinity is non-perturbative, U tends to 0 is perturbative. Now, what happened is that for the O3 model, this thing was studied not with M of L, but with what we call the second moment correlation function, right? And this was done in 1995 for the traditional model. And the idea was, again, compute some kind of 2-point correlation function, remember, in position space. You find the Fourier transform of that, and then look at the lowest momentum mode, right? So either 0 or just put 2 pi by L in one of the momentum directions. If you call this as F, this calls chi, you can actually show that there is a correlation length in any box size, L. You can actually compute, and that is the definition called the second moment definition. Now, if you think about it from what I just mentioned, you can think about this L by CL as the U scale now, because remember, M of L is like 1 over C, right? So this is your U. So if I define C of 2L by C of L, the ratio of two different box sizes, right? Substitute this here, you get that, and that is basically this function, right? And so you can plot this function versus CL by L, which is basically 1 over U, right? So if you plot this, you can actually explore basically the step scaling function. And this is exactly what these authors did, and they found this for the O3 model, right? So here is this non-perturbative step scaling function, C2L by CL as a function of CL by L. And notice this is like 1 over U. So U tends to infinity is here, so that is your IR scale where it scales to 1. And on the other side, remember, it's perturbative. So this can be obtained by just perturbation theory, right? And this particular limit will give you the UV. So if you can reproduce this function using your qubit model everywhere, then you have achieved your goal. Now, Anish, I am almost out of time. So tell me how much more time I can take.
Maybe 5 more minutes. Would that be okay?
Then let me quickly jump through. So maybe we can come back and I can show you more data here. There is some subtlety between Lagrangian and Hamiltonian methods because one was done in the Lagrangian and the other was done in the Hamiltonian. So these are all some technical details. Maybe I can explain to you So remember, we studied this loop gas, I would say, for the Wilson-Fisher fixed point, right? So we can use that same idea and add more couplings. The reason I'll show you again later on, and actually study the step scaling function for these loop gas models, which is exactly what we studied to reproduce the Wilson-Fisher fixed points and the Gaussian fixed points. And so this blue curve, remember this dotted line is exactly the traditional model for the step scaling function. This blue dots is the one that we get for this loop gas model with one set of couplings. And so notice this starts deviating from what you expect. So although in the infrared we get the right physics, so the symmetry alone is not sufficient to reproduce the UV physics. Now, if you actually add some more couplings, these cross couplings that I just mentioned, I can come back and talk to anybody about it more later on. You can actually improve this and you can get these green dots, right? So notice we can now follow this curve quite nicely all the way to this point where it's already perturbated, I would say, right? On the other hand, if you want to really push this model to these values, remember this is close to 1 and this is what was possible on very large lattices using the traditional model. So we said we should at least be able to go up till that point. And unfortunately, we were never able to reproduce these points. So all the time what will happen is I change the couplings, it'll just fall down or it'll go up. It will not try to follow this curve anymore. So we are not able to explore the UV limit, although the IR limit is fine, right? So I would say that these models do not really reproduce the asymptotic freedom that we really want. So then we said, as Simon pointed out, we'll have to explore, there are lots of couplings, and we have to explore all these coupling constant space. And if you actually think about it, there's a huge bunch of phases in these 2 qubit models, right? So there's a phase that we really want to get, which are basically spin singlets dominating. But then there are ferromagnetic phases and phases where triplets form antiferromagnets locally with some kind of dimers and all that. So this is a problem that was studied a lot in the condensed matter literature. But nobody really focused on the asymptotic freedom aspect of it. So the goal was to find what is the main phase, what is the critical point that is connected to this phase. So after a lot of trying, we said, we'll try some spin ladders. So let me tell you 2 problems that we tried actually. So again, these are some technical details. I will skip, I can come back to that if you want. So let me talk about the simplest spin ladder, right? So when I talked to condensed matter theorists, they said, let's try, the simplest would be take 2 qubits, right? And write a spin ladder kind of Hamiltonian, where J1 is the coupling for this spin half chain, J2 is the coupling for this spin half chain, and then they are coupled by JP. When JP is 0, we know that these 2 actually are critical in the sense they get very long correlation lengths. And when JP is greater than 0, you actually form singlets, and that is indeed the phase that we want. And so maybe the right thing is to study a spin ladder, either symmetric one where J1 and J2 are the same, or slightly maybe asymmetric ones, and then study the mass gap as a function of JP, right? And see whether we get the quantum critical point as I set JP to 0. Remember, as soon as I make JP small, I will get a mass gap, and that mass gap will scale to 0. So it seems like we are getting the right physics, but as you will see, the step scaling function is completely off, right? So we don't really get, although again, in the infrared, you might get the physics, but in the ultraviolet, it's completely off. In fact, it's worse than even the loop gas models. So then we finally tried something much more trivial, but still interesting. We set this chain coupling to 0, right? And this chain coupling is J. Remember, as J becomes very large, we get again, the critical point of the spin half chain. But then we set this to 1. So that sets our scale. And then we probe that model as J becomes very large. And this model did the trick. Again, these are the subtleties of Hamiltonian versus Lagrangian approaches. And here is the answer. So at j equals 3, notice I get, these are all different lattice sizes, right? At a given j, the only thing I can do is change my lattice size. And there is a mass scale generated. And then, and for very small lattices, this is, remember, this is between, oh, sorry about that. I get all kinds of phone calls, all spam calls. Okay, sorry about that. So, so j equals 3. Remember, to get this graph, I need L to do a calculation at L and calculation at 2L. So this point is at L equals 12 and 24. This is 24 and 48. This is 32 and 64 and so on. So you see, by 32 lattice sizes, I start falling on that curve. And it starts going exactly what I want, how I want. Now this is at j equals 5. Again, 12, 24, 24, 48, 32, 64, and so on. And again, I'm still off. But then as I make L big enough, around 64, I start falling on this curve. And the goal is, of course, the hope is that it'll follow on this curve. And this, remember, is symmetry. This is dynamics, right? I have to get the asymptotic freedom. And now if I make j equals 10, notice I come almost to j equals 1, which is where the traditional model was also able to go. And now again, as I come here, it sort of starts turning and it comes on that curve, right? So here, the biggest lattices are 256 and 512. Of course, we lost steam after that. So hopefully this convinces you that these Comb model, the Heisenberg-Comb, indeed reproduces the physics of this asymptotic freedom of the original model, right? And so we believe that maybe the Comb is a good qubit regularization, which is completely different from the Qubit Truncation model, right? So the Qubit Truncation will not suggest that you go to this particular theory. So you need some bit of insight about what the physics was to reproduce the physics of this. So it's say we have designed a material now which can now reproduce the O3 model with just 2 qubits on each side. So let me give you some couple of observations and then end. So notice something very interesting happening. On small lattices, we are away from the scaling regime, right? You need L minimum before L greater than L minimum to start to make sure that the theory starts falling on the curve. So this L minimum is some kind of a UV scale, right? That L minimum grows with J, right? So here is L minimum for the various J's that we have. It doesn't grow dramatically. It grows like more, maybe as a law. We haven't studied how it grows, just had 3 points. But it grows more moderately, but it does grow, right? On the other hand, the correlation length itself grows dramatically. In fact, at j equals 10, we have correlation lengths, which is the infrared mass scale, that the correlation length is 200,000 roughly, right? So we are reproducing what you really expect at an asymptotically free theory. Of course, for that, we need to go to large lattices and do this real calculation as we would usually do in a lattice field theory to convince ourselves that everything is working. Okay, so with that, let me present the conclusions. So I hope I convince you that qubit regularization is a useful idea to study quantum field theories, right? And it is very important to think about quantum field theories in this language before we start thinking about quantum computation, right? So only then we'll be able to know what theories we are doing make sense. A question, of course, is what is the smallest number of qubits per lattice size necessary to reproduce the original quantum field theory? Now, notice there was no guarantee that n equals 2 would have worked. Now, this, of course, gives us hope that maybe there's something more deeper going on, that maybe with the right kind of model or structure of the Hamiltonian, we could be able to reproduce this. So this was, I think, a helpful example, which will maybe motivate us to think for other quantum field theories. So here we were able to show that with 2 qubits, we were actually be able to reproduce the physics of the O3 model. We were able to reproduce the various scales of asymptotic freedom. And I would leave by saying that the D-theory approach is exactly the same idea, except that the qubit regularization, I believe, is a more sort of larger framework, because now you're not saying that you know the Hamiltonian itself, so you'll have to do some exploration and build your right material, I would say, to get the physics and the right quantum critical point. Let me stop there. Thank you.
So let's thank Shailesh for a wonderful talk. So it's time for questions.
I have a quick question, Anosh.
Yes, Simon, go ahead, please.
Do you understand why the honeycomb works much better than the simple ladder? Is there an intuition as to why that did a much better job?
So I think what's happening is that there is some intuitive understanding. So maybe I should just go back to my slides so that I can. So notice that in the spin ladder case, what we were exploring was the JP tends to 0 limit. And in that limit, what we get are two decoupled spin half ladders, right? And each of them is in a Wess-Zumino-Witten, this K equals 1 WZW model, right? And so we believe that what is happening is that in that system, the critical point actually is different. It's not the original critical point, because we basically are adding some kind of a relevant operator that couples the two Wess-Zumino-Witten theories. And so it's a different critical point, essentially. That's the understanding. Now, on the other hand, you might argue that in the Heisenberg-Comb, we can look at it in the same way. Why not set J to 1 and JP to 0? There, it's a bit tricky, because what happens is if you do that limit, you actually don't get a relativistic theory, because remember these points, the qubit 2 is actually frozen. So it is some completely non-relativistic, right? So it's like some crazy theory that you get, and that is not the right limit to think about. So the more natural limit is to set JP to 1 and set J to very large. And there it's very interesting that all that is happening is that this Wess-Zumino-Witten theory is being saturated at every site, or every sort of in the UV limit, by some defect. And that defect has the main effect of just removing the theta equals pi to theta equals 0. It just sort of jumps from theta equals 0 to theta equals pi. That's the best understanding we have come to so far, I must say.
I see.
There was another raised hand, but now maybe.
More questions? Jun has a question. Yes, please, Jun.
Yes, maybe I missed your point, but let me ask you. So you said that you can have just 2 qubits per site, but then you need more lattice sites. So what would be the better method practically?
Yeah, so that's a more dynamical question, which I don't know if I can answer very easily, I must say. So maybe I can try to address that. So the point I guess you're trying to make is clearly you need lattice sites before the RG begins to work, right? So you're completely right that it's possible that the more, if you put more qubits on a single site and then allow that physics to emerge, that would be a better way to do the physics. And that is indeed a possibility, that one has to sort of then do a calculation with, let's say, 4 qubits per site, and then write down the Hamiltonian maybe in a different way, and then see whether that has a better quantum circuit compared to this 2 qubit. I think that's a very good question. I don't have a very clear answer to that. But my understanding, I don't know, I'm not an expert in this, my understanding is that the more number of qubits you write per site, it's not necessarily going to improve on your quantum circuit. The quantum circuit that you want at the end, if you want to do a quantum computation, actually the model that we were motivated by was the simplest quantum circuit. In fact, I do have one slide. And in this case, the simplest quantum circuit, the S.S, can actually be implemented by that simple quantum circuit, apparently, right? Whereas if you had more number of qubits, I don't know. That's a question that has to be explored. So a priori, I don't know. I don't have a clear answer to your question.
Related to that, if you have only small number of qubits, it is possible to realize, make an analog simulator if it's like a natural condensed matter-ish model.
Maybe, yeah, that's another way to think about it, that if you have something simple, it's perhaps easier to design a material. I don't know. Yeah, these are all questions that to think about. But I think it's a good question in the sense, finally, when you try to use these to do calculations, what is a better way to do it? I would say that if you had more number of qubits, at least my Monte Carlo algorithm will be much harder. So here it's much easier for me to do this.
I mean, what you have is a trade-off between the sparseness of a lattice, right? So if you have few qubits per site and then you spread them out, then you have a sparse problem. And at least from a digital point of view, that's an advantage. But you know, it's not conceptually a totally different thing. As soon as you have a second order phase transition, a whole patch becomes locked together. And you then have lots of degrees of freedom per correlation length, right? So you always go to an infinite Hilbert space.
Yeah.
Because there's no truncation of the Hilbert space to find a number that ever gives you physics. It's a question of how you collect them together.
Correct.
And so it's a design question, which, you know, who knows?
So the way I was thinking about it was just purely academic, right? The question is, with n equals 2, so 2 qubits, can you even get this or not, right? That was sort of our more academic question. And all I'm showing you that you can, in principle, get it.
But from a digital quantum computer point of view, having a lot of qubits locked together mean you have a very complicated multi-qubit gate.
Yes.
And so maybe analog, it's a good idea, but in a digital form, it's clearly a terrible thing to have a lot of qubits. So you have to have, you know, 8 qubit gates, right?
So from your perspective, you think having n small is good from the quantum computing?
Well, it depends on the architecture. I mean, we don't know what the quantum computer is going to be. Maybe they'll have some bucket. We have lots of qubits, like we have lots of floating point numbers per site, right? After all, we always have a finite number of degrees of freedom per site, right?
Yeah.
So because classical computers have fantastically good floating point units, we just put a lot on a site.
Yeah.
But, you know, it depends on the architecture and the algorithm, right?
Yeah, agreed.
We don't know.
Sorry, my thing just collapsed. But
Shailesh, I mean, it's a beautiful result. Is it possible that if you keep going farther and farther, you would need to dangle yet another one in the comb and so on? I mean,
so yeah, one question we are exploring right now, I'm exploring with my student, is to see if we can do O4 in this way, and are there complications with just O4? So for O4, the minimal number you need, as we can easily guess, is going to be 5, right? So there's going to be a Fock vacuum, and then there's going to be the O4 vector, which is a 4-component object. So with 5 qubits, can you get the O4 asymptotic freedom? I don't know the answer for that. So if somebody knows it.
If you go back to the old asymptotic freedom idea, it was always exponentially small compared to the lattice. So, you know, could it be that you still have to keep putting more in at some small level? I mean, it's a terribly difficult problem to do numerically. Or do you have a physical insight?
That's right. So O3, we were able to do with just 2. So are you talking about O4, O5, or what are you talking about?
Well, I'm talking about what happens if you keep pushing up that curve. Are you confident that you never?
Wait. That curve you get, maybe I'm making it. This curve you get just with 2 qubits. Remember, I didn't increase my qubits here.
No, I know you did. I know you didn't, but I guess what I'm saying is I wanted to see this red curve really come down. On
which red curve?
Well,
I mean, the red thing you want to come down. Oh, then all you need to do is give me access to a bigger computer, a lot more time, and I just have to do an L124, 1024, 2048.
Very important. I guess the green curve, it looks very convincing that you're starting to follow the infrared curve, right?
Yeah.
I mean, it's very important that there's a single curve, right?
Oh, yeah. So look, this is, I think that's a bit tricky to answer. Even in the conventional model, right? In the traditional model, if I had done exactly the red kind of question, they would see exactly the kind of if you go back and look at Caracciolo's work, they do say that they only plot numbers that fall on the curve. They don't show points outside the curve. Right? So they are not plotting all the points. Maybe I should point with my thing, right? So they are not pointing. So here, I'm sure I can fill up all of these using my things, if that is what is bothering you. They do not plot these curves because they think that's not in the scaling regime. So they just drop all that.
No, I'm not worried about. What does this dotted green line indicate?
This one here. Oh, the dotted one.
Yeah.
The dotted one is perturbation theory. I think 2 loop or something like that.
Oh, I see. Okay.
The dotted line is just perturbation theory. So the dotted line fails beyond some limit here. So the dotted line, see, it's up to some particular order here.
So you're confident that as soon as you get onto this curve, that eventually in the infrared it'll follow the curve.
Yeah, that's what I'm showing, that in the orange one and the green one.
Yeah. Okay.
Here I'm just showing that it turns, but if you want me to show more points here, I'll need bigger lattices.
It's a very impressive result, Shailesh. I'm really amazed.
Yeah, unfortunately, we needed 512 lattices here. This was like huge. Yeah.
More questions? Okay, so if there are no more questions, let's thank Shailesh again.
Thank you.
And let's thank all the speakers of today's 3 sessions.